Alright, welcome back. This is the second or third attempt to record the Lecture 6. Right after that, I'll be doing Lecture 7 and Lecture 8 and posting them up on the website so that you guys have them. So what we're doing today is we're actually, what we did, last Friday, and we're covering the last part of Chapter 2, which is Coordinate Systems and Time, specifically the time systems that we use and the interplay between those. So, anyways, thank you for being patient with the technical difficulties. Let's go ahead and get started. Lecture 5 notes are posted on the website. We covered perturbed motion, if you remember. Any questions that you have, feel free to post them to the YouTube page. Here's what we're going to cover today. Coordinate systems and time. Surprise, surprise, already talked about that. So we're going to walk through precession and nutation, what those are, real quick for our coordinate frames. Earth rotation and time, and how that's related, Earth fixed and some topocentric systems, and then finally the transformation between an Earth-centered fixed and Earth-centered inertial frame, or Earth-centered fixed and J2000. And then finally, we're going to have a quick discussion about orbit accuracy before we move on to the assigned problems, which should have been completed last Friday. And again, those solutions are going out. They'll probably be posted today, actually. So look for those on the website as well. All right. So precession and nutation. What is precession and nutation? We need some rotation in order to get to a different coordinate frame. And so, I know I kind of jumped right into the middle of it, but let's say that sphere that you see on the screen is the Earth. And, well, we know the Earth is slightly tilted. Remember, obliquity of the ecliptic is 23.5 or so degrees. So any Earth-centered fixed system is actually tilted, right? Well, thinking about that for a minute, if we were to fix the Earth upright so that it wasn't tilted at 23.5 when we did our system, the first rotation would be precession, and then we would nutate, and then we would the body would actually rotate. So this is kind of body fixed coordinate system where we do 3 rotations in order to get to our frame. So maybe we rotate about Z, and now we're at our intermediate system, and then we nutate. We have a nutation angle, so maybe we rotate about Y in order to tilt it, and then finally the Earth is going to rotate about that final Z axis, and so the obviously the coordinate axes, if they're fixed on the Earth, will spin, and so that'll be our rotation angle. So there's a quick demonstration on Wolfram Alpha that I'm going to pull up real quick to try and give you a better visual of that than just using my hand as a coordinate system. So close that out real quick. All right. So this should be up on your screen right now. So let's look at it in the beginning. Nothing's rotated. Precession angle 0, nutation angle is 0, spin angle is 0, right? Okay, well, if we precess, we rotate, in this case, about Z, 45 degrees, and so we get to some intermediate frame, right? So if you notice, they try and use these loops in order to show you how things are changing, and you'll notice that the red and the blue coordinate frames have shifted from the initial frame, which is the yellow and black lines. So we've rotated 45 degrees, precessed, and then we have a nutation. All right, and so we rotate to get to that plane, or we nutate in order to get to that plane, and then we're going to rotate in that final orbit plane. So you notice now precession, that intermediate coordinate system is no longer the same as the nutation angle that we just used. And so that final frame, that body may spin in that frame, but we had to precess and nutate in order to get that to that plane, and then finally we will spin in that plane. So I hope I've given you enough examples in order to kind of understand where precession and nutation come from. But there are, the Earth obviously, the rotation angle, well, here's another quick little demonstration as well of a body fixed system using Free Flyer. So this is Free Flyer, which is available to students or for purchase if you're a professional. So we rotate about our first axis, 1, and then we rotate about our second intermediate axis, being the green, so 2, and then we'll spin in that plane. Okay, great, wonderful. Using no other angles. So the reason why we bring that up is because the the angular velocity vector of the Earth, so literally the spin of the Earth, is changing. It's our simplified model, we just fix it in direction and magnitude and call that our z, but really there's this conical counterclockwise motion which has a full revolution every 430 days, or the Chandler period. And if you remember, look at our picture again. So we're having that full motion, that it's almost like if you were to look at the rotation or the spin in the plane that it's currently in, it'll follow that precession angle around and map out a cone, right? So that'll, as you guys explore attitude transformation a little bit more and precession and nutation angle, you can actually use these cones. But our precession experiences some variation clearly, and so does our nutation, which causes this wobbly effect as the angular velocity vector precesses or rotates about the original z. So that polar motion is actually only confined to 0.6 arc seconds, so it's very small. So over a decade, or the decadal time scale, hope I pronounced that right, 10-year periods. How about that? So we can, with reasonable assumptions, simplify our model to say that the angular velocity is fixed in direction and magnitude. But clearly, this is overdetermination, and so we have to specify the accuracy to which we need, which may mean that we don't get to simplify that model and make those assumptions. When we're talking about the angular velocity change of the Earth, or the spin, the rotation of the Earth, we're talking about a change over a period required for the revolution of the Earth with respect to the stars, not with respect to the Sun. So in other words, the celestial sphere is what we're looking at. And that period change is actually expressed in a form of universal time, or delta UT1, so some variation in the universal time. It's difficult to predict the period change because, as you'll see when we use GPS or Lagos or some highly defined positioning system, we also have to include long-term our estimation of the right angular ascending node, which will change, and so the errors from the estimating where the right angular ascending node is will map into, or be essentially added to, the error in the prediction of the angular, or the error in the period change, so that change in universal time. So really we require regular observation, and those regular observations are taken and reported by the International Earth Rotation Service. So like I said, you can use your polar motion in your satellite state to estimate, but obviously the errors are in the right angular ascending node, or absorbed, or the longitude of the ascending node, or absorbed in the estimation of that change in period. How we measure our time, so kind of stepping away from that for a minute, how we use our time, or how we measure our time, because now we brought up universal time, so we want to define that. Time is different depending on how it's defined. Each event is uniquely identified by some local time or universal time. The epoch that's most commonly used right now is J2000, or in other words, January 1st, 2000, 12 hours. So if we measured it in the Julian date, we're measuring from 4,713 BC, and the day for that particular day begins at noon. So remember January 1st, 2000, 12 hours. So when our Julian day is 2,451,545 days, not 0.5, 0.0 days, right? So midnight obviously would be 2,451,544.5. So to get rid of that half-day weirdness and to decrease the amount of days that we're working with, we could take our modified Julian date, which is literally just taking the Julian date minus that's 2,400,000 and a half days. And so J2000 and the modified Julian date would be 51,544 and a half days. Remember our 12 hours. So we need a reference time because time is our independent variable. It's literally the independent variable for all the solution of the equations of motion. And every observation that we're going to take is going to be tagged with using a reference clock. So it's going to be time tagged. So typically reference clocks will use some oscillator. In your cell phone and in your watch, typically they use a crystal oscillator, but crystal oscillators are affected, have some temporal characteristics and affected by temperature. So in other words, there's some drift and some bias, especially when affected by temperature, or over time they become not as reliable. So for very high accuracy, we'll actually use atomic frequencies like a hydrogen maser or a cesium clock. And so I believe that the picture I took from there is actually one of our, there's a Precision Timing Institute established on campus, on the University of Alabama campus, and they are doing some work with a local, I believe they just got bought by Semiconductor. It's the name of the company. But anyways, so there's a Precision Timing Institute on campus, United States Naval Observatory, and the company that makes some of these masers, and they actually sell to the United States Naval Observatory. They're working on getting students up to speed on how to do some of these reference times because it's very important. It's a skill that we're losing. And so that's actually a picture of a hydrogen maser right there. So some of the various time systems that we use, obviously we've already mentioned universal time. We'll get to that in just a second. But for Earth satellites, typically we're going to use terrestrial dynamical time or terrestrial time, TT or TDT. For solar system applications, we'll use the barycentric dynamical time or TDB. And then there's international atomic time, which both terrestrial time and the barycentric time are related to the international atomic time through some specified epoch. And in order to keep the international atomic times, or the reference value of the international atomic time, we use cesium clocks or hydrogen masers and some mixture of those. So the National Institute of Standards and the United States Naval Observatory will maintain those, and Universal Coordinated Time, which is our basis for all civil timekeeping. The difference between International Atomic Time and Universal Coordinate Time is related through the change in period of the rotation of the Earth, where UT1 is equal to the Universal Coordinated Time plus the change in that period for universal time. So what's the difference between Universal Coordinate Time and International Atomic Time? The difference is that the Universal Coordinated Time and the change of period require leap seconds in order to maintain synchronization within plus or minus 0.9 seconds. The International Atomic Time doesn't take this into account, and between terrestrial time or terrestrial dynamical time, it's a simple separation of seconds. So in other words, in this case, terrestrial dynamical time subtracted, or having international atomic time subtracted from terrestrial time is 32.184 seconds, whereas the barycentric and terrestrial time difference is a periodic function, basically from relativistic effects. But the GPS time related to international atomic time, the leap second adjustments or applied to universal coordinated time, they're not used in GPS time. So we have some leap second separation. And the current leap second separation is 37 seconds as of January 1st, 2017. And that's actually, that link is to the U.S. Naval Observatory's tracking of the leap second separation between International Atomic Time, GPS, UTC, and GPS. So moving on back to our reference frames. Well, let's go back to our Earth-fixed system. So remember, we were talking about precession and nutation earlier. An Earth-fixed frame is actually hard to define since the Earth is in a rigid body. There's the lunar and solar gravitational pull on the Earth, and so it's pulling the mass of the water around, so obviously our tides, so the bodies, so the mass on the surface is actually moving over time, as well as the tectonic plate shifts. So it's not a sole rigid body. That mass deformation will physically change coordinates on the surface. It's not a sphere. So the Earth is lumpy. So a true Earth-fixed frame based solely on the body doesn't exist. However, we can define approximations and then use some reference frame, like the terrestrial reference frame, where the origin is coincident with the center of mass, and it's attached where the x-axis is coincident with the Greenwich meridian, and the z-axis is approximately, remember our simplification earlier, coincident with the angular velocity vector of the Earth. So the International Earth Rotation Service, remember those guys that are reporting back on the change in periods, they'll provide the terrestrial reference frame, or since it's the International Earth Rotation Service doing it, it's called the ITRF. There's also the WGS-84, which is used, it's a geodetic application which is used with many GPS applications. And so typically what we'll use, so expanding from the WGS-84, is actually a ellipsoid of revolution as opposed to the sphere. Remember that J2 bulge that pulls out at the equator? Well, we can actually capture that a little bit better if we use an ellipsoid of revolution. So remember, we defined our spherical harmonic coefficient in order to basically improve our model of our improve our gravitational model. Well, we're not using a sphere anymore, right? We're using an ellipsoid of revolution, so we need to convert the spherical coordinates to from geodetic coordinates to from a geocentric coordinates to a geodetic coordinate. So we actually have the geodetic latitude, longitude, and height above the ellipsoid are what we're going to use, as opposed to the geocentric latitude, longitude, and r, where r is some magnitude of the position vector. And so then the equations that are there talk about the flattening coefficient, the eccentricity of that ellipsoid of revolution that we use if we took a 2D cross-section. And h is just a relation to help differentiate between the two. And then obviously the RE and RP are the equatorial radius and the polar radius. So for our topocentric frame, so we just covered our Earth's fixed frames, right? Well, for our topocentric frame, that's physically a point that's on the Earth, on the surface of the Earth. So we have basically a local vertical plane where we have northward, eastward, and some local vertical that makes that plane, or that finishes out that triad of unit vectors. So x will be our eastward, y will be our northward, and z will be our local vertical. Well, and I've provided the transformation matrix there. You can also look this up in the textbook. And then finally, most times we'll actually use elevation and azimuth angles in order to track observations overhead. Because remember, topocentric, where are we getting our observations for the most part? From ground stations. And so the topocentric frame will define some ground station and the observations that it's taken, typically with elevation and azimuth angles as the object of interest passes overhead. And then we'll transform it out into some more useful frame like the ITRF, the International Terrestrial Reference Frame, which is an Earth-fixed frame, or, depending upon whatever application that we're working towards, in order to get back our orbital elements, or, whatever it may be, in order to either predict the satellite motion or talk more about where it will be in the future. So anyways, finally, so we've talked about our Earth-centered fixed frames, and we've talked about our inertial frames, right? Well, our inertial frames, J2000, where we have the ZXY defined by January 1st, 2000, 12 hours. And the transformation between a fixed frame and the J2000 system is actually complex because instead of just simplifying, we have to actually consider the precession of the Earth, the nutation of the Earth, polar motion from the angular velocity vector, and the universal time, or that change in universal time. And so when we're doing that transformation, as you see, the transformation matrix shown there is from J2000 to the Earth-centered fixed, where P is our precession, N is our notation, S prime is our applies the rotation in order to account for the true side real time, and finally W applies that polar motion in order to align the true pole, or the z-axis, with the pole of the ECF system, because that angular velocity vector is moving, right? So finally, a little discussion on orbit accuracy. Really, it depends on what the accuracy that you need is in order to decide how in-depth you're going to go. Because when we're talking about orbit accuracy, we're talking about the accuracy of the solution of the equations of motion with parameters in the models of forces, right? So we can break that down into two pieces, where a general perturbation technique is concerned with small parameters, or the parameters in the model of forces. Typically, you'll see eccentricity concerned because that will drive some of those small parameters in the force modeling, or special perturbation techniques where we take some initial condition that we've provided and we're solely concerned with the step size. Now, for those special perturbation techniques where we're focused on the solution technique accuracy, really our error is introduced in the equations of motion by the technique itself, and so our focus is on that numerical integration process in order to, and the step size in order to drive the accuracy of the given parameters in in order to drive that accuracy, because we're not really considering the parameters in the equation, because we've provided some initial state where we said that, you know, this is what it is, and we know it enough that it doesn't, that I don't need to be concerned about modeling the parameters in the force model. Well, force model accuracy, we're concerned with the parameters in the force model and modeling what our most significant error is. Typically, that'll end up being drag, but we want to identify that quickly and early to understand what the error in the orbit accuracy is going to be driven by. And the thing to remember is that all parameters in force models have been determined by some means. This is where the true definition of a model comes out, where it's essentially we're using something that's been simplified, so it's inaccurate, in order to give us a close enough answer about what's actually going on in the world that we can understand it and predict it, right? So it kind of drives to, really, orbit accuracy depends on what your requirement is. If you need some solution of kilometers, well, then I could probably go and use a special perturbation technique where I'm solely interested in the solution accuracy of my numerical integration, as opposed to the force model, because I need kilometers, not centimeters. But if I need centimeters, then, you know, I might be considering both of them because of the sheer amount of time that it takes to numerically integrate those force models. But my sole focus would be on getting the accurate answer, right? So I'll be more concerned with the force model accuracy. So a lot of orbit determination and getting good at orbit determination is actually figuring out how accurate do I need to be, and so making that specification, or your requirement specifications, right? So finally, these are the problems that you should have done. I'll cover them one more time, just so that you have the videos, so that those taking the class later on can go back through. So anyways, problems based on the textbook should have been turned in last Friday. Give the following position and velocity of satellite. So or given, excuse me, you're going to find the orbital elements. You're going to assume that that initial state given is okay, and that using some two-body motion, we can predict the position and velocity at t equals 3,000 seconds. Well, surprise, surprise, if we're using two-body motion, you just determined 6 orbital elements, including your mean anomaly. So, hey, let's use Kepler's equation, advance the mean anomaly, and find out what the position and velocity at that time are. Determine the flight path angle as well at that time. T is equal to 3,000 seconds later. And finally, determine the latitude and longitude of the subsatellite point for that time if the Greenwich angle and at the initial time is 0. And then you just assume that the z-axis of the non-rotating system in which those position velocities have been given is coincident with the z-axis of the rotating system. In other words, we have to convert to an Earth-fixed system in order to determine our ground track, which is what you're doing here. There are examples earlier on, I believe in 2.2 in the book, that almost walk you right through all of these steps. Problem 2, the orbit of a satellite released by the Space Shuttle Discovery, the cryogenic infrared spectrometers and telescopes for the atmosphere. It has a GPS receiver on board, and we get 2 reports back from that GPS receiver where we've taken, based on GPS time, 000s, and then 3 seconds later we get another update on the first day and the second day. Right? Great. So these are given to you in an Earth-centered Earth-fixed system. So now you know that J2 has a 95% accuracy of modeling, or excuse me, not the 95% accuracy. That's inaccurate what I just said. But it takes up 95% of all other forces that are not the gravitational parameter over r squared, right? That's 95% of our Moore potential. So what I want you to do is take those positions, those 4 position vectors that you've been given, demonstrate that the node location is not fixed in space, and determine an approximate rate of node change, degrees and days from these positions, and then you're going to compare that node rate with the value predicted by the given equation, which is also in your textbook, but I copied it there for your ease of use. Now, the thing to remember here is that the question that I got asked earlier, which is why I'm saying the thing to remember here, is where do I get my inclination from? Well, let's think about this for a minute. You've been given 4 position vectors, right? Well, when we reviewed our perturbation or perturbed motion, and we talked about the J2 models, what were the 3 orbital elements that weren't changing? I mean, they had some periods to them, but they didn't have a secular variation. It was our semi-major axis, our inclination, and our eccentricity, correct? Okay, well, I've been given 2 position vectors at least on one day in the same plane because of that, that orbital plane. The eccentricity hasn't changed, the semi-major axis hasn't changed, and the inclination hasn't changed, right? So my angle of the plane ends up changing. So I can go and determine what these should be using those 2 position vectors. Now, how would I go about doing that? Well, let's think about this for a second. We take r cross v in order to get our angular momentum, our specific angular momentum, and then take the angle of that with respect to our coordinate system, that z, in order to find our inclination angle typically, right? Okay, great, wonderful. Well, we don't have velocity. Okay, fine. What do we do now? Well, one of the things that you can do is that you can take the unit vectors of those 2 position vectors, right? Cross them, and then you'll have some unit vector that is orthogonal because both are still in the plane, they're both still in that orbit plane. That unit vector crossed will be orthogonal to that orbit plane as well. Great, and now all I have to do is find the angle between that orthogonal vector and the z. Okay, great. So finally, determine the inclination of the satellite during the first 3-second interval and the last 3-second interval. Oh wait, what I just described you have to do anyways. Hey, all right. And there's a comment about selective ability. Long story short, the selective ability from the GPS reported position is not going to affect your problem. GLONASS! Woohoo! Our third problem. Russia's answer for American GPS. Given a set of initial conditions for this high-altitude GLONASS satellite, numerically integrate the equations of motion for one day. So you're going to drive the equations of motion assuming that J2 is our only perturbation, and assume that the non-rotating z-axis coincides with the Earth-fixed z-axis. Okay. Then you're going to, during the integration, compute the Jacobi constant z component of the angular momentum, determine if they're constant, plot the 6 orbital elements over time, and then identify features similar to and different from figure 2.35. So in other words, show me the secular and the periodic variations of the orbital elements, which those will be on the solution. They'll be reproduced so that you can have a look at them if you haven't already done the homework, which you should have. And you should also have the text as well so that you can refer to it. And then finally, you're going to compare the node rate, which is predicted by that equation, with the value estimated from our 6 orbital elements as a function of time. And then finally, compare the amplitude of the semi-major axis periodic term with the given equation. Finally, plot the ground track. Does the ground track repeat after one day? Which it's a GPS. It's essentially a GLONASS, so it's a navigational satellite. So my bet is that it might repeat. Maybe not one day, but it might repeat. And then finally, the initial orbital elements are provided there. Okay, great. That's all the problems. Look forward to seeing you guys during the next lecture.